In this video, we'll discuss how you can include actual blades into the momentum model discussed in the previous video. Hence, I definitely recommend that you watch the best theory video before watching this. I will also assume that you have basic knowledge about airfoil aerodynamics, so that you have heard about lift and drag forces and phenomena such as stall, which occur at high angles of attack. The layout of the video is as follows. We will start and talk about the blade element model to describe the forces of a turbine blade, and later we will connect it to the momentum model from the previous video. We will start by ignoring the turbine for a while and instead study a single airfoil. As an example, let us assume that we are studying a sailboat and we are looking at it from above. We assume that the sailboat is going to travel to the right in the figure and that the incoming wind has a 90-degree angle relative to the boat's motion. At the beginning, the boat is standing still. To make it a bit more similar to a wind turbine, assume that we use an airfoil instead of a traditional sail. For simplicity, I have chosen a symmetric airfoil, even though you can get better performance with the more advanced airfoils. The lift and drag coefficients of this airfoil can be seen in the figure. The green line is the lift coefficient and the red line is the drag coefficient. Alpha is the angle of attack, which at the moment is 0 for this blade. The initial peak for lift is at 12 degrees angles of attack, and drag force starts to increase significantly at about 15 degrees. This is what we call stall, which decreases the blade performance. The data we see in the figure is measurement data for the NACA 0012 airfoil, which is the airfoil that is drawn in the figure. Now, change the angle of the blade to get an angle of attack of 12 degrees. We can see that we get a lift force pushing the boat forward. The drag force is so small that we cannot see it. Recall that the relationship between the lift force and the lift coefficient is that the lift force is 1/2 times the lift coefficient, fluid density, blade area and velocity squared. Now, to illustrate the drag force, increase the angle of attack to 30 degrees. Here, we have stalled the blade and get a drag force illustrated in red. As long as the boat is standing still, the blade will still be pushed forward and the drag will just tilt the boat. We will later see that for moving boats, the drag will have a significant negative impact. Note that the lift and drag forces are just two components of the aerodynamic force. Here we call this aerodynamic force F. The drag force is calculated in the same way as the lift force. Hence, we use the index L/D to indicate that the formula works for both indices. To show what happens for higher angles of attack, let it go all the way to 90 degrees. Here, we only get the drag force. Let's return to the case with 12 degrees angles of attack. Now, let the boat start moving and call the speed of the boat V blade. What we saw here is that as soon as the boat started moving, the lift force disappeared. To analyze this case, let's move to the moving reference frame of the boat. We will also hide the boat and only look at the blade to get a more clean look. Start by checking the velocity vectors in this moving reference frame. First, draw the incoming wind speed v wind in the same direction as the wind. Second, add the speed of the blade in the opposite direction as the blade is moving. Negative sign comes from that if you're moving to the right, you will experience an incoming wind from the left due to your own motion. When we add these two together, we get the relative wind speed. We can see that the relative wind speed has the same direction as the blade. Hence, we get 0 angle of attack and thereby no lift force for our symmetric airfoil. To get the lift force, we need to change the angle of the blade. First, we go back to the base position with the blade in the same direction as the wind, which for a stationary blade has 0 force. Now we have a force in the direction opposite to our motion, which would stop the motion. If we instead pitch it to an angle of attack that is 12 degrees with respect to the new relative wind direction, we get our forward pointing lift force back, and the blade can accelerate to even higher velocities. In this video, the length of all vectors are drawn to scale with respect to the other vectors of the same variable. Now we are going to look at blades that move significantly faster. As the force grows with the square of the relative velocity, we need to adjust the scale of the force vectors before moving forward. Assume that we keep an angle of attack at 12 degrees all the time. So when the blade speed changes, we change the pitch angle of the blade to compensate. Let the movement speed of the blade increase. As the lift force is always perpendicular to relative wind speed, we can see that its direction changes when the blade speed is increased. We will introduce the name VREL for the relative wind speed. The magnitude of the relative wind speed can be calculated from the Pythagorean theorem. It is the relative wind speed we should use when calculating lift and drag forces. Call the direction of the relative wind speed the angle of relative wind. This will be denoted by the variable phi, which can be calculated using Arcus tangents. We can now define the pitch angle as the angle between the chord line of the blade and the direction of the blade motion. Call the pitch angle theta p. The angle of attack is still the angle between the blade chord line and the relative wind speed. Directly from geometry, we see that the angle of attack can be calculated as the difference between the angle of relative wind and the pitch angle. To illustrate how the angles change, watch what happens when the blade speed changes. Let us look at the direction of the lift force. We can see that only a small part of this force is currently pointing in the direction of the blade motion. It's only the component of the lift force that is pointing forward that will move the blade forward. Call the projection of the aerodynamic force in the direction of the movement the tangential force, Ft. The tangential force can be calculated from the lift force by multiplying it with sinus of the angle of relative wind. We can also add the normal force, which is the component of the force perpendicular to the motion of the blade. This force is calculated using cosinus instead of sinus. Watch what happens when these forces when we change the blade speed. Both the lift and the normal force increases almost quadratically when the blade speed is increased. But there's only a linear increase in the tangential force. This is due to the factor sinus phi, as the angle of relative wind decreases with increased blade speed. But it is still a linear increase, so when the blade moves faster, the force pushing it forward increases. So what is preventing it from accelerating to infinite speeds? We will of course have other forces, such as from the boat resistance against the water, but let's ignore those and only look at the blade. Now we need to bring back the drag force, which will give a braking force on the blade. We also need to update the equations for the tangential and normal forces to include drag. Here I want to stress that we only have one aerodynamic force, F. We can either choose to describe this force as a lift and drag force, or we can describe it as a tangential and normal force. Going from lift and drag to normal and tangential forces is just the rotation of the coordinate system. using the angle of relative wind as our rotational angle. To get the more illustrative values, let's increase the drag by a factor 10. We can see that the drag force is reducing the tangential force, while it has almost no effect on the normal force. Now, watch what happens when the blade speed increases with this new drag force. When the blade speed increases, the drag will give a larger contribution to tangential force than the lift force. This is due to the projection with the angle phi. Cos of phi will be almost 1 at high blade speed, while sine of phi decreases, which will cause drag to dominate for sufficiently large blade speed. Let's zoom out and see how large the normal force is for this case. To find the maximum speed that the blade can accelerate to, decrease the speed until the tangential force is 0. To show how the drag affects the maximum speed, let the drag force double once again. Let's zoom out and find the new movement speed that gives 0 tangential force. We can see that the maximum speed is lower when we increase the drag. Hence, if you want to design a wind turbine that rotates at a very high speed, you need a blade profile with low drag. This is one reason why the old windmills used large blades and rotated slow. Back in those days, they didn't have blade with as low drag as we have now. Let's restore the drag force to the values from our measurement data. I want to mention that the measurement data is for 2D, and blades do in general give better performance when 3D effects are neglected, hence the low drag. As a next step, let's illustrate what happens when we increase the blade speed, but keep the pitch angle constant. As we draw all forces to scale, let's zoom in on the center of the forces, which for the blade that is not stalled is at the quarter chord position. This is 25% from the leading edge of the blade. First, decrease the blade speed to 0. We will now be deep into the stall region and will thereby have a large drag. When the speed is fast enough to avoid stall, we will see a significant increase in the tangential force. Then, when the blade speed is too high, the angle of attack becomes negative and we get a tangential force in the opposite direction. Let us show one more case, but with a lower pitch angle. Now, basically, we do not have any tangential force when the blade is standing still. So to get blades with low pitch angle moving, we need to give them some speed first. When we reach some speed, the blade starts to generate a tangential force and will work significantly better at high speeds. In all cases we have kept the wind speed constant and only changed the blade speed and the pitch angle. For the real case, the wind speed can change as well. As a final case before we leave the single airfoil, let us think how we can control the forces to avoid too large tangential forces when the wind speed increases. This is very important for wind turbines when we have too large wind speeds. I will now illustrate the concepts used for wind turbines for this individual blade. The first concept we are going to look at is passive stall. This was used in the early wind turbines before more advanced methods came. First, assume that the movement speed of the blade is constant. This limitation comes from that generators needed to rotate at a fixed speed to match the electric frequency of the grid. With passive stall, we'll also assume that the pitch angle is fixed. This means that we can choose any pitch angle we want during the turbine design, but we cannot change it once the turbine is operational. All turbines will have a rated wind speed. If the wind speed is larger, we reduce the tangential force to reduce the turbine power. Assume that it is the wind speed shown in the figure that is the rated wind speed. To get passive stall to work, Choose a pitch angle to get an angle of attack very close to the stall angle at rated wind speed. Now, watch what happens when wind speed changes. We start from 0 wind speed. As we let the wind speed increase to the rated speed, which is 1 here, note that the lift force increases approximately linearly with the wind speed. This will give a quadratic increase in the tangential force as the angle of relative wind also increases linearly. Hence, sinus of phi gives another linear contribution. If anyone thinks this is strange that it's quadratic and not cubic, as the power increases with the cube of the wind speed, and the power is the tangential force multiplied by the constant rotational speed, you need to include that for a turbine. The thrust force will reduce the flow speed through the turbine, as we saw in the best theory derivation. Hence, later when we include the momentum theory, we will see the cubic growth. Now, to show passive stall, watch what happens when the wind speed is increased above the rated speed. The angle of attack becomes so large that the blade will stall and the tangential force decreases and will eventually become negative. Hence, by choosing the angle of attack close to the stall angle, we got a turbine that automatically reduced its power at too high wind speeds. The disadvantage is that we cannot control the tangential force. Hence, we cannot keep a constant power above rated wind speed. Later, turbine manufacturers started to add pitch mechanisms to the turbine. This allows the blade to turn during operation. Now we can use this to reduce the power to any value we want. There are two options now to reduce the power. If we operate at the optimal point, turning the blade in either direction should decrease power. Let us start with the first direction and turn the blade to stall it. This is called pitch to stall. Watch as the tangential force decreases when you pitch the blade to stall it. Note that you only need a small change in pitch angle to get a very large effect of the blade performance. Let us also take a look at what happens if the wind speed increases while the blade is at this pitch angle. We see that the blade is pushed deeper into stall and the tangential force remains negative. I want to comment on that I pitched the blade way too much in this case, just to illustrate how it works and how sensitive it is. In reality, you only want to pitch enough to reduce the tangential force, not to make it negative. My second comment is that the blade has a relatively large drop in lift force. Other profiles can give higher lift force in stall. The other option when we pitch in the other direction is called pitch to feather. Here we lower the angle of attack to decrease the lift force. This has the advantage that it typically gives smaller normal force. However, if the wind speed increases, the angle of attack will increase and we get a larger tangential force. A very simplified description of the difference between the two is that pitch to stall reduces the tangential force by increasing the drag force, while pitch to feather controls the tangential force by decreasing the lift force. So, which one is most commonly used? It is pitch to feather, as it generally gives lower total forces on the blades. One should also mention that when a blade is in stall, it will experience fluctuating forces due to the vortices generated behind the blade. This, combined with the larger forces for pitch to stall, is why pitch to feather is the preferred option. There is yet another way of controlling the forces if the turbine can vary its rotational speed. By decreasing the rotational speed, one will stall the blade at the same time as the lower velocity decreases the force. Here, if the wind speed increases, it will push the blade into even deeper stall. The disadvantage of this method, though, is that due to the turbine inertia, it takes much longer time to change the rotational speed than to pitch the blade. Let us leave power control and continue and adapt our single blade to an actual wind turbine blade, which has a rotating motion and hence a radial dependence. This will be the blade element model. We will leave the momentum part for later. As there is a radial dependence, we need to split the blade into several radial segments. If the segment is small, we can approximate the constant radius over a single segment. The idea is that we want to use our 2D theory that we used for a single airfoil for each of our segments. Basically, what we are doing is a form of numerical integration over the blade. Let us choose one segment to study. We call it segment I, and for all variables that are unique to this segment, which are the variables that vary with the radius, we put an index I to them. This is very similar to what we did in the wake rotation video, but this time we are only looking at a single blade. Call the length of the segment delta R and the chord length at this segment Ci. The area will be the chord multiplied by delta R. Now, let us look at the velocity vectors. At the initial state, we will assume a general velocity field and call the velocity Vni for the normal velocity and Vti for the tangential velocity. We want to look in the rotating frame though, as this is the reference frame that the blade itself experiences. Hence, R omega is added in this direction. We will neglect the flow in the radial direction as the aerodynamic force in this direction is small, simply because the area that the pressure can act on is very small in the radial direction. The relative wind speed is calculated using the Pythagorean theorem as before. We add the angle of relative wind as before, which is calculated by arcus tangens. Note that this angle is also the angle of relative wind phi. A second way of calculating the relative wind is from the normal velocity and sinus phi. In the blade element model, we do need the flow velocities to calculate the forces. Hence, we need to couple this model to a model that can calculate the flow velocity, if we know the forces. There are multiple models that we can choose from. We have two main categories. The first is to use computational fluid dynamics and solve the full velocity field using a computer. The advantage is that one can handle complex flows, include terrain, see how turbines interact, and much more. The disadvantage is that it's computationally expensive. The first approach here is the actuated disk model. Here one approximates the turbine as a flat disk with a pressure drop similar to our best theory. The flow can be either stationary or one can run the simulation time dependent. The second common approach is the actuated line model, where one assumes that blades are linear force distributions. This will give a more realistic flow field, but will be more computationally expensive. We will not go any deeper into these models in the video, so consider this a brief orientation into the possible options. Instead, we will use a model that is very fast and much simpler to implement. That is the momentum model, which is the same model we used in the previous video, when we derived the best theory and the wake rotation. In this model, we describe the flow velocity at the turbine using the induction factor A, which describes how much the flow is slowed down by the turbine. V in is the undisturbed flow velocity. This is what you will have when a turbine is not operational. Update the expression for the relative flow velocity using the actual induction factor. Update the expression for angle of relative wind as well. In the tangential direction, we had the angular induction factor A'. Update the flow velocity using the angular induction factor. And update the angle of relative wind. Let us now recall the local tip speed ratio, which is the speed of the blade divided by the incoming wind speed. Multiply and divide by V in squared to obtain the local tip speed ratio. V in can now be placed outside parentheses. This expression is 1 over the local tip speed ratio. The forces are calculated using the same expression as we had before. The lift and drag coefficients are mainly functions of the angle of attack alpha, but it will also have a small dependence on the Reynolds number, as larger Reynolds numbers generally give a slightly larger angle of attack before the blade stalls, and the drag coefficient at low angles of attack is usually lower for high Reynolds numbers. The Reynolds number can be calculated as the relative wind speed multiplied by the chord and then divided by the kinematic viscosity. A common approach is to use experimental data when determining lift and drag coefficients, which was the approach used earlier in the video when we looked it up in the graph of the coefficients as functions of the angle of attack. The angle of attack is the angle between the relative wind and the chord line, and is calculated in the same way as earlier in the video. We will now call the angle of the movement direction and the blade chord line the section pitch angle. This angle can be divided into two parts, the blade pitch angle and the section twist angle. The blade pitch angle is the angle used by the blade pitch mechanism and can thereby be adjusted during the turbine operation. This will be the same for all segments though, as we only have one pitch mechanism per blade. The section twist angle is the built-in angle which can vary between the segments to optimize the turbine performance, but it cannot be adjusted during turbine operation. The lift and drag forces can be converted to tangential and normal forces by rotating the coordinate system with the angle of relative wind in the same way as before. Let us merge the equations starting with the tangential force. We have a common factor. Multiply both sides by Ri. Radius times tangential force is the torque. Insert the area. Here we need to count for the number of blades as well, as 3 blades will have 3 times as large area as 1 blade. Reorder. Let's do the same for the normal force. Same common factor. Same area. Reorder. Now we have the expressions we need to calculate the normal and tangential forces, as long as we know the actual and angular induction factors. To calculate the turbine power, use that power is rotational speed multiplied by the torque and sum over all the segments. To calculate the thrust force, use that it has the same direction as the normal force. Hence, all we need to do is sum the normal force over all segments. Our current issue is that we need to know the induction factors. To calculate those, we are going to use the momentum equations we derived in the previous video. We do need to account for the blade segments though. Assume that you have a turbine with a given cross-sectional area. We will now divide this area into equal number of segments as we did with the blade. Now we are going to study the circular segment which contains our segment I on the blade. If we want to include that variations in incoming wind speed, as the wind speed increases with height, we should also divide the flow domain into azimuthal directions. Now we can set different incoming wind for different segments. The torque and normal force expressions need to be adjusted. First, we have two directions. Add an extra index j to the variables that vary with azimuthal directions, which are most of them except the radius and the chord. If the azimuthal step is constant, we can also update the torque by distributing it among the segments, simply by dividing with the number of segments. The power will now be calculated as a double sum. In terms of mathematical complexity, the difference is very small, as the size of the segment will be cancelled later anyway, so the expressions derived will basically be the same, but computationally we'll have to solve it for a much larger number of segments. Considering that we are most likely to do it in a computer, this method is so fast that one should not worry about the computational time though. The same modifications can be made for the normal force and the thrust force. To make the text in this video a bit cleaner, I will drop the double indices here though, and neglect this azimuthal variation. In the previous video, we derived the following equations for the torque using conservation of angular momentum. As this equation is for the flow field, the area will be the circular segment. This is the circumference 2 pi r multiplied by delta r. Combine this. The second equation we had is for the thrust, which we derived from conservation of momentum. Note that the thrust and the normal forces are the same. The area is the same as in the previous equation. Now we are going to start by deriving a simplified expression for the optimal chord. We will make the assumption that optimal performance is achieved at the same actual induction factor that gave the best performance in the best theory, which is 1/3. We remember from previous video that this gave the optimal thrust coefficient 8/9. The key element in the blade element momentum model is that we set the thrust from the momentum theory equal to the thrust from the blade element theory. All these cancel. Note especially that delta r cancels. This would have happened even if we would have divided the area into azimuthal segments as well. Hence, the expression after would be the same independent on how we create our segments. In this simplified model, neglect the drag forces. Insert expression for the relative wind speed. V in cancels. Again, use that the optimal actual induction factor is 1/3 according to Betz theory. This becomes 4/9. Combine all constants. Split this square. Cosinus over sinus is 1/tangents. Use the expression for angle of relative wind. Take tangents of both sides. Use that A is 1/3. 1 minus 1/3 is 2/3. We are also going to neglect the wake rotation in our simplified model. This means that A prime is 0. Insert expression for tangents. Combine the constants. Multiply by sinus. Solve for the chord length. We also want to calculate the optimal blade twist. Here we will assume that the blade pitch angle is 0, which means that the section pitch angle and the section twist angles have the same value. Solve for the section pitch angle. Rewrite in terms of arcus tangens again. And insert into the equation for the section pitch angle. Remember that the blade has an angle of attack that gives optimal performance. Hence, we want to keep a relatively constant angle of attack along the blade. The pitch angle would therefore mainly be affected by the angle of relative wind. Let's go back to our plot of the blade and study the results of these equations. The plot on the top right represents the shape of the blade. The length is normalized to 1 and the proportions should be correct. The graph on the top left is the optimal pitch angle along the radius. The red marking illustrates which position that is currently shown for the blade. Right now it's the blade tip that is shown. For simplicity, we assume that the entire blade is constructed with the same airfoil, as we used in the single airfoil case. The wind is set to 2/3, which is the normalized value for optimal at A equals 1/3. Current tip speed ratio is 5, and we have 3 blades. We will now watch an animation when the radial position changes along the blade. Notice how the blade becomes larger and the pitch angle changes when the radius decreases. Let us watch what happens when we decrease the number of blades to 2. The optimal pitch angle stays the same, but the chord is increased and so is the forces. The reason the forces increase is because we split the same total force between 2 blades instead of 3. We are going to watch the animation once again for this case. This time, note that the tangential force is almost constant when the radius changes, while the normal force varies linearly with the radius. This can be expected since we assume an even drop in pressure over the entire disk. We also assume even power absorption. As the area of the segment is 2 pi r, delta r, and hence increases linearly with the radius, the normal force increases linearly as well. The constant tangential force is explained as the torque that generates the power, and torque is radius times tangential force. Hence the torque increases linearly as well. We can also look at the one-bladed solution. It should be obvious that the optimal chord is only theoretical and that it's not realistic to build a turbine with this large chord. The normal approach is to deviate from the optimal chord for low radius to reduce the mass and size of the blade. Let's go back to our 3-bladed turbine and change the tip speed ratio instead. Increasing the tip speed ratio gives a smaller optimal chord. Let the radius vary again and observe what has changed when we increase the tip speed ratio. Note that the normal force is almost the same while the tangential force is slightly lower. If we go to an even higher tip speed ratio, we see that the blade becomes very small. This can be problematic from a mechanical point of view, as the structure needs to handle the large bending moments generated. Let us again return to tip speed ratio 7, which is a typical value for a turbine. We will now look at what happens if the lift coefficient changes. This can be achieved by changing the design angle of attack. Here, the forces remain almost the same while the optimal chord increases. Before we continue with the more general solutions to the blade element momentum model, there are some additional corrections we need. The first we are going to look at is three-dimensional effects and induced drag. We start by a repetition of what induced drag is. Here we see an airfoil pass through a plane full of blue particles initially at rest. When the blade passes through the plane, watch what happens at the blade tips. The red line represents the blade tip vortices, which always are created behind the blades. They will cause the flow to start moving downward behind the airfoil. They are also drifting downwards themselves as they introduce a velocity on each other. Note that we need to push the flow downward in order to generate a lift force according to momentum conservation. Hence, we need to have these tip vortices present. A traditional explanation of the induced velocity is as follows. The blade travels to the right and the lift force is pointing up. The tip vortices give an induced velocity downward, which will change the direction of the relative wind, causing a lower angle of attack and a change in the direction of the lift force. We can adjust the pitch angle of the blade to compensate for the change in angle of attack, but a new direction of the lift force will have a component pointing backwards. This will therefore act as a drag force and is what we call induced drag. As we previously had lift forces pointing downward, we can change it here as well, to make it more similar to our previous case. Now, the induced velocity is pointing upwards instead. How does this relate to a wind turbine? Let us ignore the induced velocity for a short while and go back to our wind case. The induced velocity should be in the opposite direction of the lift force due to momentum conservation. Hence, it will look like this. We can see that if we add the vectors together, the effective wind speed is reduced, while the speed in the movement direction is increased slightly. This should remind us of our axial and angular induction factors, which have the same effect. Hence, we can make the conclusion that the induced velocity is the contribution from the axial and angular induction factors. Considering that we have used momentum conservation to describe both the induced velocity and the velocity reduction in the turbine wake, it is quite feasible that both actually are the same effect. Does this mean that we already have accounted for induced drag in our model? In a way, yes, but the situation is more complicated and there are more effects that needs to be accounted for. Let us take a look at the tip vortices for the airfoil again. If our simplified model with fixed induced velocity is correct, what we would expect is a constant downward velocity due to the tip vortices released behind the blades. What we can see though is that the flow is circulating around the tip vortices with higher flow velocities close to the center of the tip vortex. We have to assume that this distinct tip vortex will cause additional effects that has to be accounted for by our model. We should also account for that the blades are moving in circles and not in straight lines. Here we have a simplified approximation of a rotor. We have the outer tip vortices and the inner vortices close to the center are called root vortices. I want to remark that this is a simplified model where the entire root vortex is released at the same position. But in reality, as we do not have optimal chord all the way to the center, the root vortex will be distributed over a larger area. Hence, the wake rotation is slightly overestimated in this simplification. I have also neglected wake expansion to make it visually easier to follow. To understand how vortices affect the flow, let us watch a simplified two-dimensional approximation of the tip vortices released by the blades. First, observe that the flow velocity is much larger above the vortices than below. Hence, tip vortices can be used to describe the reduction in flow velocity in the wind turbine wake. In this illustration, the distance between the vortices will be decreased. At the same time, the strength of the vortices are reduced correspondingly. So when we have twice as many vortices, the strength is reduced to half to keep the average strength per length constant. For a wind turbine, this will correspond to adding twice as many blades and reducing the chord by half, hence keeping the average normal force constant. In this illustration, I have made the vortices very small, which will give high velocities close to the center. The vortices are also moving on a fixed line, while in reality this configuration is unstable and would decay, which is one of the mechanisms behind the decay of the wake. Note that the closer the vortices are together, the more it looks like a jump in flow velocity. This illustrates the assumption of infinitely many, infinitely thin blades in the momentum theory. That is the case without additional losses. If we go back to the original case with the relatively few vortices, we see that the flow is moving up and down between the vortices, which will cause additional losses. The larger the distance we have between the tip vortices, the more significant losses can be expected. Turbines that have many blades and turbines that rotate faster will have shorter distance between the vortices and hence can be expected to have lower losses due to the fact that vortices are separated from each other, instead of a continuous heat. So, how do we correct for this effect? The derivation is too complicated for this video, so I will just give you the expression for the correction factor F, which we will use to account for the tip vortices. This is a factor between 0 and 1. If it's 0, no power will be generated, and if it's 1, the turbine will operate without any additional losses. To include this into our model, we must update the momentum expressions. We do this by simply multiplying with F, starting with the equation for the torque. Do the same for the thrust force. The given correction is only for the tip vortices, which are the most important ones. To create an equation for the root vortices, use the following values for the radius instead. Let's restore the equation. To complete the model, we need an expression for the actual induction factor A. We will derive this by setting the two expressions for the thrust force equal. Start by cancelling the density and delta R. Use the expression for the relative wind speed. Cancel V in. Divide by 1 minus A. Let's combine these terms. This is what we call the solidity, here denoted as sigma prime. The solidity is a measure of how large part of the swept area that is covered by the blades. Once means that the combined blade area is equal to the swept area. Expand this parenthesis. Reorder. A is a common factor. Divide all terms with this factor. This is 1. Solve for A. Divide by the solidity. This expression allows us to calculate the actual induction factor if we know the angle of relative wind and lift and drag forces. A common approximation here is to neglect the drag in the calculation of A. This is a good approximation unless we have stalled the blade. We will keep the full expression for now though. Remember from the previous video that the expression for thrust has limitations. First, note that there are 2 possible solutions for a given thrust force. You should therefore check that the value for A is below 0.5 and not the symmetric counterpart. When I made the plots for this video, I did encounter the false solution with a high actual induction factor for some cases when I started from an actual induction factor above 0.5 for the wind speed calculations. So watch out for it. We do need a better expression in the case for large actual induction factors. The course book by Manwell, which this lecture is based on, suggests to use Glover's empirical relation between the thrust and actual induction factor. This correction should be used if the actual induction factor is above 0.4, or one can use the condition that the thrust should be above 0.96. The equation works well for F equals 1, but watch what happens when F decreases. As we clearly see, the 2 curves will no longer overlap, and for a range of thrust coefficients between the 2 curves, there is no solution for A. This will give us trouble as the blade element model can give these thrust values. This will give strange output when calculating A. I will therefore recommend that we use another model that do not have this issue. One model that can replace Glauer's empirical model is the model by Boole. I will put a link to it in the description. It will give about the same curve when F equals 1, but watch what happens when F decreases. This model is designed to always have a continuous derivative at the transition point. Now, each thrust coefficient will have a unique corresponding actual induction factor. This is sufficient for our current purposes. If your plan is to in detail study turbines operating at this high actual induction factor, you should use CFD models for the flow. Here, we only want a model that gives reasonable results in the full interval. Let us continue and derive an expression for the thrust coefficient that we use in the model. Start from the definition of the thrust coefficient and insert the area for the segment. Then use the thrust force from the blade element model. The density and delta R cancel. Insert expression for the relative wind speed. The velocity cancels. Combine these. We see that they are the solidity. We now have an expression we can use to calculate the thrust coefficient. Finally, we need an expression for the angular induction factor. Start from the expression for the torque from momentum model. Set this equal to the torque from the blade element model. The density and delta R cancel. Again, we combine these. Which is the solidity. Insert expression for the relative wind speed. The velocity 1 minus a and r cancel. Combine this. This is the local tip speed ratio. Combine this. Multiply and divide by 1 plus the angular induction factor. This is tangents of the angle of relative wind. Tangents is sinus over cosinus. Sinus cancels. Expand this parenthesis. Reorder. A prime is a common factor. Divide all terms with this expression. This is 1. Solve for A prime. Now we have all the equations we need. It is time to go through the steps of the blade element momentum model. This model will calculate the forces and the power for a given turbine. It's a very efficient model for getting good estimates of the performance of a turbine. Before we start, we need to choose the geometry of the turbine that we will study. As we divided the turbine into segments, we need to solve for each segment. We can start by calculating the solidity and the local tip speed ratio, as those are independent of the induction factors. The induction factors will have to be solved numerically, as we cannot expect any analytical solution, especially due to the evaluation of the lift and drag coefficients. Therefore, start by making initial guesses for these. An example of a starting guess could be the optimal values for the factors, or if we previously solved a similar turbine, that solution could be used as an initial guess. Now we are going to iterate to a solution for the induction factors. Start by calculating the angle of relative wind and the relative wind speed. Now we can calculate the Reynolds number and the angle of attack. These will be used to determine the lift and drag coefficients. The easiest way is to use experimental data for these coefficients. This is how I did it earlier in the lecture for a single airfoil. Now we want to evaluate the thrust coefficient and the correction factor F. This will allow us to determine which model for the actual induction factor we should use. For the angular induction factor, we use the same model in all cases. Now we check for convergence. This is done by comparing the values for the induction factors we had in the beginning of the loop and our newly calculated values. If we calculated factors are the same as the initial values, we have convergence. Otherwise, continue the loop. If we have convergence, leave the loop and calculate the force and the torque for the segment. When we have looped over all segments, calculate the power and the thrust force. This is done by calculating sum over all our segments. Now we have done, and we have estimated the performance of the turbine. If we want the power coefficient and the thrust coefficient, just use their definition. This particular method works because we assume that the segments are independent. If you use a more advanced force model, such as a force model with time dependence, you could get coupling effects between the segments. In that case, we need to swap the order of the two loops and place the segment loop inside the convergence loop. This is too advanced for this video though. I also want to mention that this particular method will not always converge. This is a standard problem of solving nonlinear equations though, so you can try another numerical scheme if you're experiencing convergence issues. Now we're going to run the model and see what we get as results. This method will use the equation I just showed. The minor modification I've done is that I have limited the actual induction factors to values between 0 and 1. I also implemented the bisection method for increased convergence. Here, I will only plot the results for a single segment. Assume that our turbine has 3 blades. It is designed for tip speed ratio 7. It uses the same airfoil as we used in the entire video. It is designed for an angle of attack of 9 degrees to give some margin to stall. We start by plotting the segment at 75% of the full radius. The chord and section pitch angles use the optimal values as we derived earlier. This gives the following chord and pitch angles. The dashed line represents the Betz limit. The purple line is the calculated power coefficient. The green line is the thrust coefficient. The blue line is the actual induction factor. We can see that both the thrust and the actual induction factors increase with the tip speed ratio, while the power coefficient peaks slightly below 7. Note that the graph shows the turbine tip speed ratio, which always is calculated using the full turbine radius. Let us look at the position closer to the turbine center. Now we can basically see a jump in the power coefficient at tip speed ratio 6. The short explanation is that the blades stalled at tip speed ratio below 6. To explain the jump, we need to remember that the blade element model is a steady state model. When the blade stalls, the actual factor decreases. This pushes the blade deeper into stall, which causes the jump. In reality, if the tip speed ratio changes past this jump, the speed of the whole wake would have to change before we reach the steady state conditions. Hence, we can expect a much more smooth transition in reality. It can also be noted that the chosen airfoil has poor stall characteristics with a large drop in lift force when it stalls, which contribute to this jump in power. I also want to mention that the equations can have multiple solutions, one in stall and one without stall. Therefore, I will add thin lines where I designed the code to look for solutions at higher actual induction factors. We can see a small region with multiple solutions around tip speed ratio 6. Let us go all the way down to segment radius 10%. This is the point where drag forces do contribute to the induction factors, which explains the large actual induction factor and the thrust force at low tip speed ratio. Now, watch what happens when we slowly increase the radial position of the segment. In the beginning, we see that we get better performance when the radius increases, which is what we expect due to wake rotation. At the end, though, we lose performance due to the correction factor F. It should be noted that I only included the tip correction and not the hub correction in this model. Let's go back to 75% of the radius, where the correction F is small. Now, watch what happens when we decrease the blade chord length. We see that the peak power coefficient occurs at higher tip speed ratio in this case. Let us do the opposite and increase the chord instead. This pushes the peak power coefficient to low tip speed ratios. I want to remark that we have kept the pitch angle constant while doing these changes. This high chord case is a good illustration that we need to adjust the pitch angle to get good turbine performance. Let's return to our base position. Now we're going to test and change the pitch angle to illustrate power control. First, let us test pitch to feather and decrease the angle of attack. This initially moves the peak power coefficient to slightly larger values. Note how both the power and the thrust force decreases. Let us return to the base position. We will now try pitch to stall and decrease the angle of attack. Note how the stall point moves to higher tip speed ratios. We can also observe that the thrust force at high tip speed ratios get very large. I want to remark here that when we use power control, we will be at high wind speed, hence the tip speed ratio will be lower than normal. You should therefore not put too much focus into what happens at high tip speed ratio in this case. Let's return and end the demonstration. This is the end of the main description of the blade element momentum model. As this video is designed as a lecture with Manwell's wind energy explained as course literature, there are some parts in the book that I think require further explanation, as it can be hard to follow the derivations there. This is caused by the omission of many steps which are left as exercises to the reader. I will therefore add more detailed derivations of several equations here, with focus on how one can derive the more advanced expression for the optimal chord with the wake rotation included. For the first equation, while we were deriving the expression for the actual induction factor, we had this expression during one step. Go back in the video if you want to see how we got it. In the book, the drag force is neglected for all calculations of the induction factors. Divide by 1 minus a. Divide by 4f. This is our first equation. During the derivation of the angular induction factor, we had the following expression. Neglect drag again. Sinus cancels. Divide by 1 minus a. Divide by 4f and the local tip speed ratio. This is our second equation from the book. Now we want to combine them. Move these to the other side of the equality. This is tangents. Move these to the other side of the equality. The right-hand side is now equal for both equations. Insert the second equation here. Reorder. Here we have a second equation relating the angle of relative wind with the two induction factors and the local tip speed ratio. This is actually the equation telling us that the induced velocity has a 90-degree angle with respect to the relative wind speed. This means that it's in the opposite direction of the lift force, which is exactly what we assumed when we talked about the tip vortices which induce the velocity opposite to the lift force. Hence, this expression confirms our earlier assumption about the relation between induction factors and tip vortices. Let us also derive the equation for the lift coefficient. Place these alone on the right-hand side. Separate these. Insert the expression for the angular induction factor. We still neglect the drag force. Sinus cancels. Reorder. This is a common factor. Insert our relationship between the induction factors. 1 over tangents is cosinus over sinus. Write 1 as sinus over sinus. Multiply both sides by sinus. Solve for CL. This is yet another equation from the book. Now we're going to calculate the power coefficient. Start from the definition. The area is pi radius squared. Insert expression for the power. Insert the expression for the torque. For power calculations, we need to keep the drag force. 1/2 times the density cancel. Insert expression for the relative wind speed. We will now make the assumption that the inlet speed is the same for all segments. Multiply both numerator and denominator with the rotational velocity squared. Combine these. This is 1 over the turbine tip speed ratio squared. Combine these. Multiply and divide by 2 times radius. We can now identify this expression as the solidity. Place rotational speed and radius next to each other. Place inlet velocity next to them. This is the local tip speed ratio. Let's call this term delta lambda. Rewriting this is very similar to variable substitution when we solve integrals. Write 1 sinus inside parentheses. Sinus cancels. This is 1 over tangents. Multiply and divide by CL. Write CL outside parentheses. Reorder this. Split this square. Let's bring back this equation. Move these to the other side of the equal sign. It is now equal to this expression. Insert a new expression. Combine. This is the first expression for the power coefficient in the book. Now comes the part that is complicated and therefore left as an exercise to the reader. There may be easier ways of doing it, but at least I found one way. Insert expression for the angular induction factor. This drag force can be neglected as it's part of the induction factor. Sinus cancels. Multiply by this. Now insert expression for the actual induction factor. Neglect drag force. Multiply by this. Now we want to write the expression with a common denominator. These two cancel. Let's bring back the expression for the lift coefficient. Move solidity to the other side. We can now replace this with our recent expression. For F cancel. We want to write this with a common denominator. These two cancel. Now this is a common factor. We know from our trigonometric identities that sinus squared plus cosinus squared is 1. This can be moved to the denominator. We can cancel 1 lambda r. Now move this to the other side, which now has become equal to this expression. Insert it. Let us revert this equation to its previous state. We can now insert it here. Sinus cancels. We want to write this with a common denominator. These cancel. Combine these into one division. This is 1. For F cancel and move the remaining expression to denominator. Reorder these. To get the same expression in the book, convert this into an integral. The limits are from the tip speed ratio closest to the hub to the turbine tip speed ratio, which is at the blade tip. This is the final expression for the power coefficient. The book suggests to use this expression to calculate the power coefficient with the blade element momentum model. I do, however, still recommend to just calculate the power as I explained earlier, and then using the definition of the power coefficient to normalize it. I prefer the previous way, as that method works for large actual induction factors as well, while for this model we did not account for the empirical correction at high actual induction factor. So why is this equation still useful? It's an equation for the power coefficient that basically only depends on one variable. Since we can choose any angle of attack by changing the section pitch angle, we can consider the lift to drag ratio of the airfoil as a constant that we maximize. Therefore, our only variable is the angle of relative wind. So if we want to find the optimal performance, we only need to find the optimal angle of relative wind. As the correction factor f is relatively complicated, we will likely need to solve this equation numerically in its current form. If we introduce some simplifications though, we can derive expression for both the optimal angle of relative wind and the corresponding optimal chord. Here we will assume that the correction factor is 1 and that we can neglect drag. Neglecting drag will give too high power coefficient, but we assume that that effect on the optimal chord is much smaller, which makes it a reasonable approximation. As usual, when we want to find the peak value, we find where the derivative is 0. This optimization is done for each segment individually, just as before. Set derivative to 0. We can remove the tip speed ratio as the expression is 0. Now, let us recall the product rule for differentiation. Call sinus squared f of I, the second term g of I, and the third term h of I. As the derivative is 0, write 0 here. We can now note that the derivative of g of I is minus h of I. We can also note that the derivative of h is g. F of phi is a common factor. Insert expression for h of I. Expand the square. Remove parentheses. Insert expression for g of I. And expand the square. These can be combined. Place first in the parentheses. Insert expression for g and h. Expand the parentheses. Insert f of I. And insert df d phi. As we cannot generate power if the angle of relative wind is 0, we can assume that this is a false root, and thereby divide by. If we look closely, we see that these two are in the same form and can be combined. These two can also be combined. And finally, these can be combined as well. The local tip speed ratio is a common factor. Now we see that this is a common factor. Lambda is a common factor here as well. Use that sinus squared is 1 minus cosinus squared. Combine the cosinus terms. We do the same thing here. If we remember our trigonometric identities, we know that this is cosine of the triple angle. And this is sinus of the triple angle. Move to the other side. Divide by this. This is tangents over 3 phi. Let's make a substitution. Call lambda 1 over t. Multiply by t squared. This is t. We are now going to use Weierstrass substitution. Call tangents of theta over 2 t. We know that tangents of theta is 2 over 1 minus t squared. If you want to see the proof, just look up Weierstrass substitution on Wikipedia. We can now see that these two expressions are identical. Hence, we can identify theta as 3 phi. Solve for t. Insert into our Weierstrass substitution. We can write it in terms of arcus and solve for the angle of relative wind. This is our new expression for the angle of relative wind, where wake rotation is included. Now, some of you may think, couldn't we just have used our optimal induction factors we derived in the previous video and inserted into the equation for phi? I have checked it numerically, and it will give the same angle of relative wind. So now, I leave it up to the viewer to prove that it actually is the same. Instead, I will continue and derive the equation for the optimal chord. Let's go back to almost the beginning. Divide by h squared. H cancels. Insert expression for f of phi. And the expression for df d phi. Let's bring back the equation for the lift coefficient. We assumed earlier that f is 1. Move to the other side. Identify the denominator as g of phi. Identify denominator as h of phi. We can now insert the expression here. And here as well. This is a quadratic equation, and we know the solution for those. As the left-hand side is positive, this has to be a plus. This expression is 1. Reorder. Insert the expression for the solidity. Solve for the chord length. This is our final expression for this video. As a comparison, let's bring back the optimal equations without wake rotation. We will now plot the difference. Let us start from a high tip ratio of 15. We have 3 blades and designed for 12 degrees angle of attack, which gives highest CL. Start by the old chord, add in the new expression. We can see a clear difference at small radial positions. Close to the blade tip, they are almost identical. We see similar trends for the optimal section twist. Now let the tip speed ratio decrease to 7, which is a more common design value. We see a larger difference for low radial positions, but the trends are similar. We end by going down to design tip speed ratio 4. Now wake rotation will start to affect the optimal shape for most of the blade. The conclusion is that close to the blade tip, neglecting wake rotation is okay, but we should include it closer to the hub though. But to be realistic, it would not be practical to use as large chord as predicted anyway. As the new expressions are basically as simple as the old ones, the recommendation is of course to choose the expression that include wake rotation when choosing the design. With this, I will end the video. Thank you.